So last time we talked about the fact that if you draw an angle bisector, you have AB times AC equal, for example, AE times AD, right? And today we're gonna talk about something that is not quite obvious and something that most other people may not think about. AB times AC, that looks okay. However, AE times AD, I want you to pay some more attention to this. Is a very common type of configuration that shows up in geometry. A product of two segments coming out of one point on the same direction, on the same ray coming out of A, right? AE and AD are colinear, right? This is something looking similar to like a power of a point. Imagine if there is a circle passing through E and D, okay? So let's just say there's a circle like this. Then AE times AD is the power at point A, right? AE times AD, no? The power at point A with respect to this circle. So on the right-hand side, there seems to be a circle hiding. We don't know which one. We're not sure, not quite sure yet. Which one are we talking about? Not quite sure. On the left-hand side, there's an AB times AC. Maybe that could give us some hint of to locate this circle. Just this AB times AC is problematic. Why? Because they're both coming out of A, but they don't exist on the same ray, right? They're not collinear. They don't go in the same direction. So the problem is, what can we do to find this circle? Or in other words, what can I do to AB times AC to make it look like a power of a point? Well, one thing fundamentally is that I have to put them on the same direction. They need to be in the same line, right? For example, now we are thinking, right? So if I extend AC, or I extend AC to a point F, such that AB equal AF. Now what? Now AB times AC equals AF times AC. That is power of a point at point A, right? And that also equals what? AE times AD. Now what do you see now? So AE times AD equal AF times AC. What does that mean? This means DECF, cyclic. It's a cyclic quadrilateral. This quadrilateral DECF is conscribed on the circle. DECF, they exist on the same circle. So I could draw a circle like this. All right, it's interesting, no? How would you normally prove a quadrilateral is cyclic? If you don't think about power of a point, if you don't know that we have this behind the scene, right? And how else would you prove this? That DECF exists on the same circle. Normally, we would have done something like angle chasing. So if you're watching this, you can think about it. You can pause the video for a moment and think about it. Why is this quadrilateral cyclic? In the meantime, let's look at a better graph. All right, so angle chasing. All right, I suppose that if you don't use PowerPoint, you probably have to go chase some angles. For example, I would have connect EF first because I think there is a pair of congruent triangles right now. Which one? This side equal this side, right? AB equal AF. This angle equal this angle. AE is a common leg that's shared. So this triangle is congruent to this one, right? SAS. And so this angle equal this angle. To prove a quadrilateral being cyclic, you just need to find a pair of inscribed angles. So seeing this angle, I suppose that we should think about this one here. Is this angle the same as this? Yeah, because this one is equal to this. Because they both facing the arc of AC, right? AC's inscribed angle, this one or this one, they're the same. And so now we have this angle equal this angle, and we're done, right? DECF is cyclic. That's nice. Interesting, right? Something you don't think about, but if you see a segment, a form that looks like possibly a PowerPoint, you should think about it. All right, now there's another pair of identities here. For example, DC square equal DE times DA, right? DE times DA is the power at point D with respect to a circle passing through E and A. So maybe something like this, right? DE times DA, no? Power at point D versus this circle. But then you have a DC square. What does that mean? This is a very strong indication of a tangent, right? Think about it. So if you have a circle and there is a point outside and you draw a tangent, and in the meantime, you draw another chord, something like this. Say this is D, this is E, this is A, this is C, right? Then you know DC square equal DE times DA, right? Classic tangent condition. And that's exactly what's fitting here, no? That seems to be the case right here, right? So I suppose if I draw the circle that's passing through EA, not only that, that circle should pass through C. So if I draw the circumcircle of ACE, then DC should be a tangent to this circle. DC is tangent to this circle at point C. That's interesting, no? Right, let's look at a little better graph. Which is here. This one. Okay, so if you draw the circumcircle of triangle ACE, then DC should be a tangent. Now, if DC is a tangent, it means that if the center of this circle is point P, suppose, okay? So if you draw this radius, then it's supposed to be perpendicular, right? If P is the circumcenter of triangle AEC, and you connect PC, then PC should be perpendicular to DC. If you claim DC is a tangent, right? Now, so pause the video for a second. Do you think this is correct? Can you prove this? I mean, I would have proved it already by using PowerPoint because I know this, but if you don't know about these angle bisector properties, you probably have to do some angle chasing, all right? So pause the video for a second, think about it. How would you prove it? If you want to prove PC perpendicular to DC, we probably could do something like this. So now this angle PCD is like cut into two parts, right? So there's this angle part here, and then there's this angle here, right? PCE, right? If I draw a perpendicular here, I'm trying to figure out what's the value of PCE, all right, the angle PCE. So if I draw a vertical here, I see that this angle is the same as this. Right, because this is half of the central angle of arc CE, right? And this is the inscribed angle of arc CE. Yeah, so they are equal, right? But then this angle equals this and equals this. And so this one plus this one equal 90 degrees, right? Because inside this triangle, inside this right triangle here, they add up to 90, right? And that's it. So this plus this is 90. No? That was easy, no? But anyway, it still takes a little bit of time to think it through, right? Something behind the scene. All right, if you don't know the angle bisect, the power of a point, these hidden messages that's given, you know, you would have to do some angle chasing, right? But if you see the PowerPoint connections, then you can recognize these properties right away, right? That's the benefit of thinking about in that direction, right? All right, so I want to wrap it up by introducing a practice problem. This one, it was a problem of last year's AMC 12, problem 24. All right, so let's see. Triangle ABC has three sides. Bisector. Oh, so let's draw a graph. B, A, C. This is 11. This is 24. AC is 20. Bisector of BAC cuts BC at D, cuts the circumcircle at E. The circumcircle of BED, okay. Talking about which one? They are talking about this triangle here, triangle BED, okay? Let me highlight it. They are talking about this triangle. The circumcircle of this triangle intersects the line AB at a point F. So if you draw a circle of this passing through these 3 points, it's going to meet AB at another point. Suppose here. F. So like these 4 points are on the same circle. What's CF? Pause the video for a second. While I draw the graph, supposedly, you don't even have the graph. You have to draw it by yourself. All right, so pause it and think about this problem. And so I hope by now you should see clearly in a couple of seconds that AC equal AF. That's the whole point I talked about today, because AB times AC equals AD times AE, right? But then knowing that EDBF is cyclic, we must have AD times AE equal AB times AF, right? So AC equal AF. So this is 9. All right. Well, okay. So what's next? I'm seeing a isosceles triangle here. ACF is isosceles, right? AF equal AC. And what else do I need to know to figure out CF? I think maybe the cosine of this angle, maybe. If I know the cosine of this angle, I could apply law of cosine inside triangle ACF, right? How would I find out the cosine of this angle? What about using triangle ABC? No, I know the 3 sides. Cosine BAC equal what inside this triangle? 11 squared plus 20 squared minus 24 squared divides 2 times 11 times 20. Law of cosine, all right? And if you check it out, the value is -1/8. Don't take my words. You're going to have to verify yourself, all right? And once you are here, the rest is easy, all right? So okay, so now I can apply again the law of cosine in triangle ACF. That's an easy one because it's isosceles. So CF squared equal 2 times AC squared, no? 20 squared minus 2 times, well, AC times F, it's again 20 squared, times the cosine of this, 1/8. Change the sign to plus. This is a square here. And that's 900. All right, so CF equals 30. All right, so if you know the property of angle bisectors and stuff, this is, at least to me, a couple of seconds that you could recognize. The fact that they put this, the circumcircle of triangle BED intersects the line AB at another point. That makes the problem kind of, oh, that looks scary. Oh, it looks difficult, but it's not that bad, right? If you are prepared, if you have been practicing, all right? All right, guys, have fun, all right? If you like what you're seeing, please subscribe, all right? And stay tuned for more updates. Thank you all. Bye-bye.